All right, so let's start the afternoon session on simultaneous information and energy transmission. And I would like to start answering one interesting question I got during the lunch regarding the use of the acronym Simultaneous Wireless Information and Power Transfer. The question in particular was why we are not using that acronym despite the fact that this is widely used, and instead we are using something else. Well, the answer is simple. That acronym is unnecessarily long. We can take away the word wireless because these results apply to both wired systems and wireless systems. Second, there is a misuse of the word power. So we are transmitting energy from one point A to one point B, and then the power can be seen as the rate at which the energy is being transmitted. So essentially, the word energy and power cannot be used indifferently. And then the third reason is the word transfer. Well, in our community, we prefer the use of information transmission instead of information transfer. And in general, whenever electrical signals are involved, we prefer the word transmission instead of transfer. I mean, this is despite the fact that in physics we can talk about energy transfer. All right, so now we can start in common grounds. I think now it is clear why we are not using what most of the authors in our community are using to call this technology. I would like to start acknowledging that this is joint work with Selma Beladjamor, one of my postdocs during 2016 and 2017. Nizar Kalfet, that is a PhD student in his last year, and then Professor Ioannis Kikridis and Professor Vincent Poor. All right, so let's start with this example that I like a lot from the University of Washington. So there, what they did is that they hacked this Wi-Fi access point to be constantly transmitting information packets, and the energy containing those RF signals is gathered by this antenna to power up this camera that is taking photos from time to time. Here it is very clear we are using RF signals to power up a device. There is no information transmission here because despite the fact that this is a communication system, an information system, we are only powering up the camera here and not telling the camera where to take the photo in time. So this is, let's say, a good example, but we are missing there the information transmission to this device. In general, during this afternoon, we are going to be concerned with the communication systems that are engaged with two objectives. One, that is information transmission to a point A, and energy transmission to a point B. The points A and B can be collocated or not. This is completely transparent for the models that we are studying here. All right, so the afternoon is going to be divided in two parts. In the first part, we are going to study point-to-point communications and multiple access channels. And in the second part, we are going to be tackling decentralized systems and presenting the open problems that we have in this area. All right, point-to-point channels. So what we have here is a very simple diagram explaining a point-to-point communication. So we start by picking up a message index M from a set of cardinality bars M. Here is the notation. We assume that it is bounded, and the logarithm in base 2 of that number divided by the number of channel uses is indeed the rate at which we are transmitting energy. So how it happens? Well, we give N to the encoder. The encoder picks up a code word that we denote here by XM, and at each channel use, one of the components of this vector enters the channel, and we observe at the output an output that we call Y. After N channel uses, we have a vector of length N that we use for estimating the message index that we have transmitted. So the estimation is denoted by M hat, and the message index, the true sent message index, is denoted by M. So the event in which these two estimation and true index are the same, we say that the communication was successful. In the case it is not, this is an error event, and the probability of that error event is what we denote by probability of error. So we are going to be taking care of this event. We would like this probability of error to be very small. from the energy transmission point of view, we are assuming that the channel has an extra output that we denote by S, that is connected to the energy harvester, and there is a function omega. This function omega takes every channel output and give us the energy that we can gather from that channel output. So we have here the sum of all pieces of energy that we have gathered during all n channel uses, and we denoted by omega n of the output S. And then the average energy rate at which we have harvested the energy is denoted by B n, and it is indeed 1 over the total number of channel uses times the total energy that we have gathered. All right, so the event that we are going to pay attention here is indeed the average energy being smaller than B is indeed an energy outage. So the probability of that event is what we will call probability of outage in the rest of the afternoon. And clearly we want this probability to be sufficiently small. We say that if both objectives are achieved, meaning we are transmitted at an information rate that is R and an energy rate that is B, and both the probability of error and the probability of outage go to 0 with the block length, we say that we have built a code that achieves the rates R and B. And then the set of all rates, information rate and energy rate, is what we are going to call the information and energy capacity region. Well, we are going to see that later. First, let's review the work of Lav Barshney here. He was one of the first information theorists tackling this problem, and in particular he said, well, what is the maximum amount of energy that I can transmit given that at a given point B I have to satisfy a minimum energy rate? Well, this is what we have here. So he said, well, that amount of information is indeed the maximum of the mutual information between the channel input and the channel output. So this is what we see here, optimized over all possible probability distributions over the input that satisfy that the expectation of that Bn, that was the average energy rate, is bigger than B, which is the minimum that we need to satisfy at the energy harvester. Well, if this optimization problem can be solved, then we divide by n and we take the limit of n going to infinity, and it turns out that if that limit, I mean, for ensuring that limit exists, we have to take the Lin sup, and then that number is going to be called C of B. So this is essentially the maximum information rate that can be achieved given that a minimum energy rate B is asked. And then he has proved indeed that this number is the maximum that we can achieve. And this was indeed one of the very first, let's say, information theoretic analysis of this technology. So let's go through a very simple example. What we see here is binary symmetric channel with probability of error P. Essentially, 0 is converted into a 1 with probability P, same for 1 being converted into 0, and the bit arrives error-free with probability 1 minus P. Let's assume that the output that is connected to the information decoder and the output that is connected to the energy harvester are the same. So this is what we are assuming here, S is equal to Y. And then let's analyze the system from the information transmission perspective only. All right. So the maximum amount of information that we can transmit is indeed the maximization of the mutual information between X and Y, input and output, over all possible probability distributions that we can have at the input. Well, if we go through the calculation, we are going to see that the capacity, at least the information capacity, is 1 minus the binary entropy evaluated at P, which is the probability of error. And that capacity, that information capacity, is achieved when the input is Bernoulli distributed with parameter 1/2. Essentially, the code words contain the same number of zeros and the same number of ones. Okay, so from an information point of view, this is what is happening. We have to transmit essentially with Bernoulli inputs, and we will obtain the maximum information rate. Well, from the energy transmission point of view, this is what we can say. The maximum energy that we can ensure at the energy harvester is indeed 1 minus P, right? And this is achieved when we are transmitting all ones. In particular, because we have assumed that the energy gathered by an output 1 is equal to 1, and the energy gathered with a 0 is equal to 0. We are assuming that these two let's say channel outputs carry different amounts of energy. I will make a comment of what happens when these two are equal later. So let's assume that case first. Well, it turns out that this is the maximum energy rate that we can achieve. This is achieved transmitting only once. And then if we are transmitting with Bernoulli Q inputs, the rate is going to be this one that we see here, B of n. Right, with n sufficiently large. Okay, so let's apply the theorem of Barsney, and we see that that optimization problem is can be written exactly as this. We want this Bn to be bigger than B, and we want to maximize the expression that we saw before over Q, which is the probability of a 1 when we are building our code word. All right, so let's see. What we see here in the vertical axis is an information rate, and what we see in the horizontal axis is an energy rate. So what we can see is that we can transmit at the capacity of this channel up to a given energy rate, which is 1/2. 1/2 is the energy rate that is achieved when we are transmitting with Bernoulli 1/2 inputs. If we want to transmit more energy than what is achieved with the optimal information inputs, well, we are going to start decreasing the information rate, but we can see that we can achieve indeed the maximum 1 minus P when we are transmitting only once. So essentially, when we want to transmit more than what is achieved at the information optimum, we have to transmit more ones than zeros, and then this forces us to reduce the information rate, but it allows to transmit more energy. This is essentially the trade-off that we have, and this is something that was pointed out in the work of Lab in that first paper at INSA. Okay, we can see another example. This is a Gaussian memoryless channel. We have a Gaussian channel through the information decoder, and also a Gaussian channel through the energy harvester. Well, the signal that we see at the information decoder is the channel input times the channel coefficient plus a Gaussian noise, and something similar happens for the energy harvester. We assume here that the noise at the information decoder and the noise at the energy harvester are Gaussian distributed and independent. Well, what we can see? The capacity of this channel from an information point of view is achieved when we transmit with Gaussian inputs with variance P and mean 0. And then this is the rate that we can achieve. What is the maximum energy rate that we can achieve? Well, this is 1 plus SNR. Let's see what happens here. So if we try to solve the problem stated by Barsney in his paper, well, we will end up that the energy constraint is not active whenever we have a power input constraint of this form. And then optimizing with or without the energy constraint is exactly the same. So for any feasible energy rate B, the information rate is the capacity of this channel. So in this case, what we see is that there is no trade-off between the information rate and the energy rate. This is very surprising, at the first glance, but not at the end, because what we see here is that this expression of mutual information is monotonically increasing with the power that we put to the channel inputs. And this is exactly what maximizes the energy that we can gather at the energy harvester. So these two, let's say, objectives are aligned, and that's why in the optimization problem, there is no competition between these two constraints, and we can transmit at the information capacity of this channel, despite the fact that we are requiring a minimum energy at the harvester. Well, this was very interesting, and then my colleague Bruno Clerks and his group studied this, and they studied the case in which they take into account the non-linearities of the amplifiers. And then they say, well, the function that is going to tell us the energy that we gather at each channel output is not going to be x squared, the squared function, as we assumed in our analysis. We are going to assume something that looks more realistic. And then they took that function, they expanded in a Taylor expansion, and they took not only the first term, which is the x squared, but all the other terms. And it turns out that when those terms are taken into account, well, again, this trade-off between increasing information rate and decreasing energy rate appears again, and this is done in this very interesting paper. Okay, so that gives us a glance of what is going on in the point-to-point case. We have pointed out to the interesting papers in that domain. Let's see now what happens when multiple users are involved. Well, the first thing that we need to take into account is that we are going to talk about then a volume that is going to contain in some dimensions the classical dimensions of information rate, so R1 and R2 if we have two users, but we will have an extra dimension that is going to be the energy gathered at the energy harvester. So we will have everything as we have had before, plus at least one additional energy rate. And I say at least one because we may have several energy harvesters, but for the sake of simplicity here, we are going to assume that there is only one. And this is exactly what we have here. So what we are seeing in this slide essentially is two transmitters transmitting information to one receiver, and an energy harvester that is placed somewhere around that uses the same RF signals for gathering some energy for recharging a battery that we see there. We require then, the main requirement is that the information transmission must take place, but we need to satisfy this minimum energy rate B. All right, this is the main assumption here, and what we see here is then a more developed diagram of this communication system. We see in red a multiple access channel from transmitter 1, transmitter 2 to the information decoder. So there is here the Gaussian noise, and then the channel coefficient are all around here. And what we see at the energy harvester is another multiple access channel. So the signals that we see there are the weighted sums of the outputs of the transmitters plus a noise. Again, we are assuming this independent. ZT and QT are Gaussian distributed with variance 1 and 0 mean, and they are IID. All right. So there is an input power constraint, and then we put it here. So the average power in the code words is bounded by a number that we call PI max for transmitter I, and the SNR at the information decoder is here. So okay, so one is the index used for the information decoder, and 2 is the index used for the energy harvester. So what we see here is the SNRs measured at information decoder and the SNRs at the energy harvested. All right. So we start by assuming that there is a common randomness, and this is denoted here by omega. And it is going to play a fundamental role. It is a random variable that is given to the information decoder and both the transmitter 1 and transmitter 2, and it is going to play the role of a common randomness. For the information transmission, we know we don't have the need of that, but we do need this for the energy transmission. So from the information transmission point of view, now the event that we need to take care of is whether or not the estimation that we do of the message index M1 and M2 are the same at the information decoder. If the event takes place, then we say that then this transmission was successful, and if not, we declare an error, and the probability of that error is that what we are going to denote as P of error, R1 and R2, because it is going to be dependent, of course, on the block length and the rates R1 and R2, which are the information rates of transmitter 1 and transmitter 2. All right. So from the energy point of view, we can say that the maximum energy that we can gather is indeed 1 plus the contribution of transmitter 1 and the contribution of transmitter 2, plus a term that speaks about the correlation between these two signals. That correlation is obtained thanks to the fact that we have common randomness. So when the signals are fully correlated, we obtain this energy rate. All right. Keep in mind that we have defined SNR as the product of square of channel coefficient times power. So the noise here is variance equal to 1, and then here what we mean is not a ratio that is without units, but rather the product of the channel coefficient times the power. So this has units of energy. So energy of the noise, contribution of transmitter 1, contribution of transmitter 2, and the contribution of the correlation between these two signals. All right, so the average energy rate is indeed the square of the output seen at the energy harvester, and we divide it by the total number of channel uses to obtain an energy rate. So the event at which we are going to be paying a lot of attention is whether or not this average energy rate is less than B. When that average is less than B, B being the rate, the energy rate at which we want to operate at the energy harvester, when it is less than B, we declare an energy outage, and the probability of that event gives us the probability of energy outage. So naturally what we would like is to build systems that indeed reduce sufficiently this probability of energy outage. As in the previous case, if we are satisfying both objectives, meaning we are transmitting at information rates R1 and R2, and the probability of error goes to 0, we say that we have a reliable information transmission. If we have an energy transmission at rate B and the power outage at that rate goes to 0 as well, we have then a reliable energy transmission. If we satisfy both, then we say that we are simultaneously transmitting energy and information in a reliable manner. All right, so this is the first result that we obtain. This is the information energy capacity region, and it is parameterized by the 4 SNRs that we have. So essentially, 2 SNRs can be measured at the information decoder with respect to transmitter 1, transmitter 2, and another at the energy harvester with respect to transmitter 1 and transmitter 2. We need to pay attention here to the indices. Remember, 1 is used for information, and 2 is used for the energy harvester. All right. So the first result consists in all possible information and energy rates that can be simultaneously transmitted. So if the rate R1 and R2 and B are achievable, they satisfy these 4 inequalities. Okay, for those that are used to the multiple access channel, the first 3 inequalities look like more or less the same except for this beta 1 and this beta 2. There is a 4th inequality that is new, and then it is equal to the contribution of the noise, contribution of transmitter 1, transmitter 2, times a term that speaks about the correlation between the signals being sent by transmitter 1 and transmitter 2. All right, so for going more into the details of this theorem, let's analyze what these terms beta 1 and beta 2 may mean. Let's try to get an intuition of that beta 1 and beta 2. Well, let's first put beta 1 and beta 2 equal to 0. In that case, R1 and R2 are upper bounded by 0, meaning there is no information transmission. But what we see in this upper bound is that indeed it is going to be maximized. So from that perspective, we already may imagine that beta 1 and beta 2 has to do with this trade-off between information rate and energy rate. Let's see when it is equal to 1. When it is equal to 1, then we obtain exactly the same expressions that we have in the multiple access channel without any energy constraint. In this case, this term is going to be 0, and we will be obtaining the contribution of the noise plus the contribution of the two transmitters, and nothing is obtained from the correlation of the signals, meaning the two signals are indeed independent. So already we can make a claim. I am not going to get into the details of the proof, but I will give you all the insights that we may get. So already with this analysis of beta 1 and beta 2, from an achievability point of view, we can then imagine a system that is built as follows. There are two signals, one that carries information, and let's say that we are going to build it as Cover and Weiner told us in the 70s. And there will be another signal that is built using the common randomness, whose role, let's say, is going to be only the energy transmission. We are going to sum up this signal, and this is the signal that we are going to be transmitting. Well, it turns out that that simple, very simple scheme is indeed an optimal transmitting scheme. Because if we go from a converse point of view, and then we study these inequalities using Fanon's inequality, we obtain the first three when we have this division, and a concentration inequality, a very simple concentration inequality, give us this upper bound on B. Okay, the details are in this paper. I'm not going to go into the details, but I just want to highlight that this is the construction is essentially having two signals. Both of them carry energy. The signal that is carrying information carries also energy, and there is another signal that carries only energy. All right. So with that in mind, we can pass and then see the shape of this volume of this information energy capacity region. Well, what we have here is rate of transmitter 2 and rate of transmitter 1, and then the vertical axis is the energy rate. All right. So let us try to play with this volume to take some more conclusions about this first theorem that we have stated. All right. So if we see this figure from the top, what we are going to see is that we see the pentagon that we saw once in the analysis of the multiple access channel without any energy constraint. Indeed, this is the identical. This is the exact pentagon that corresponds to the capacity region of that channel. And then when we see this from one of the sides, we see that that pentagon goes up to a certain point, and after it starts shrinking here, we can see up to a point at which it becomes only 1 point with information rates equal to 0 and maximum energy rate. All right, so let's see a little bit the numbers for us to have a clearer idea. So we have the points Q1 and Q2 that are telling us exactly those points are in the pentagon. I cannot actually see properly this, but those points are in the pentagon of the multiple access channel, and what we see here then is how this actually shrinks up to this point. All right. So let me get closer and then see these points, because this is actually very interesting. So Q1 is a point that we achieved at zero information energy, at zero information rates and maximum energy rate. We see the points right here and the point here. Information wise they have the same coordinates, but we are at a different energy rate. So what we are seeing here is that, as we saw in the point-to-point case, there is a threshold. So we start transmitting our information at this point, and we obtain a given energy rate. But if we want to transmit beyond that energy rate, we are going to start reducing the information rates that we may achieve. And this is something that we saw in the equations. This beta now is playing a role. What is this exact point then? This exact point in which there is this breaking point. Well, this is the exact point at which the signals being transmitted by both transmitters are independent. That's why we can transmit any point in the capacity, in the information capacity region. As long as we start correlating these signals to gain that extra term that we saw for the upper bound of B, we need to correlate the signals. This reduces the amount of information that we can transmit, and up to a point at which we arrive to zero information but maximum energy transmission. All right, so these are essentially the takeaway messages. We have presented the full characterization of the information energy capacity region. We have seen the important role played by the coordination in the sense of correlation between the signals, but we have also seen that cooperation is not natural. We need to give some common randomness to both transmitters in order to obtain that increase in energy. This is something that from the information point of view is not needed. That correlation is not needed. But we are going to see that from a purely communications point of view, that cooperation, that correlation may appear as a result of something that is very familiar to us, which is feedback. So let us see the effect of feedback in these scenarios. Well, consider essentially the same multiple access channel that we were studying at the beginning, but assume then that the backward link, the feedback link, is used to provide to the transmitters the exact channel output. Basically, what we are assuming here is that the backward link has a capacity that is sufficiently large for us to transmit a copy of the same signal that the receiver uses to decode the message indices. All right, so this is a very extreme assumption. This is known as channel output feedback, but this is let's say from the perspective of looking for the limits of the systems, the assumption that is going to give us the fundamental limit of simultaneous information and energy transmission with feedback. All right, so with that justification, let us see in more detail the system. What we see there is the exact system we had before. Now with the link of feedback, we see the channel output is sent to both transmitter 1 and transmitter 2. And from the information transmission point of view, the big difference that is being made now is that if I have a copy of the output at transmitter 1, I can subtract the signal sent by transmitter 1 and obtain a noisy version of the signal transmitted by transmitter 2. I say noisy because we still have the noise that we have at the input of the information decoder. So at least partially we could recover the message transmitted by transmitter 2 at transmitter 1, for instance. Hence, if we have an opportunity to observe the signals being sent by transmitter 2, we can use them to generate the channel inputs later in time, and then a correlation may appear between transmitter 1 and transmitter 2, because transmitter 2 can do exactly the same. He also receives a copy of the channel output. All right, so now the message that we have to keep in mind is that there is the correlation due to omega that is still given to everyone, and another that is due to a correlation obtained by feedback, right? Keep in mind the following question. What if we don't have omega? What if we don't have the feedback? We have already answered that question. And then let's see whether or not this omega is absolutely needed. All right. So the result is the following in this case. We again have the three first bounds that are very similar to those of the multiple access channel with feedback, right? With the exception that we have again a beta 1 and beta 2, but we also have another term that is rho. We have a fourth term that is a bound on the energy rate that contains actually the term that we saw before, which is exactly this one, times the square root of this term, plus a new term, which is 2 times rho of something that also speaks about the correlation of the signals. We are going to see this more in detail in a while. I'm not going to bother you with these proofs, but it builds on the work, of course, made by Ozarov in multiple access channels with feedback. So we go through a construction that is more or less the same for the information carrying signal and another signal that is exclusively carrying energy. For the proof of converse, we are using again Fanos inequality and some assumptions on the fact that the transmitted signal may or may not have a non-zero mean and a given variance that now become parameters, and this is what allows us to obtain exactly the same expressions from the achievability point of view and from the converse point of view. All right, so let's say the volume that we obtain now as an information energy capacity region is the following, and there is a big difference now. We see that the Pareto front of this volume is now bigger. We have obtained a point Q6 that is way higher than the one we were obtaining before. But let us see this by parts. So let's see this from the top. This volume seen from the top is this one, and this figure corresponds exactly to the information capacity region shown by Ozarov in his paper in 84. So essentially what we see here is that without constraints, so this is when the energy rate that we request is 0, we obtain exactly the same information capacity region. All right, when we see now this from the side, we see that there is indeed a trade-off. For some points, it starts at this point, and for other points, it starts later here at Q6. So let's see this Q6. So there is a point in the Pareto optimal front here, which corresponds actually to the point at which we are achieving the maximum sum rate between R1 and R2. And this is very interesting. If we are at that point, which is the maximum information sum rate, we can start increasing the demand of energy rate. We pass the point at which we are transmitting with independent signals, and then we achieve a point that is higher. Well, that excess, let's say, of energy rate that we obtain is due to the fact that to achieve this point in the information domain, we require some correlation between both signals. All right? So that correlation that is needed for increasing the information sum rate actually helps a lot to increase the energy rate as well. So that's why we have a Pareto front that is elevated, let's say, or is bigger than what we had only when we have the simple multiple access channel without feedback. So very interesting. Two key points, two key ideas up to here. We need correlation, let's say artificial correlation due to the omega random variable that we saw, common randomness, for achieving these points that are on the top of this volume need correlation. Now, in the case of feedback, achieving some Pareto optimal points information-wise require correlation. That correlation then help us to achieve higher energy rates. Now, this of course has a limit because the feedback is noisy, remember that. So for us to transmit fully correlated signals, we need to get to know a better sample of the signal of the other, and then the omega, the common randomness, is still needed to achieve the point Q1. All right. So all these points that has an energy rate smaller than Q6 can be achieved only by the correlation due to feedback. If we want to go beyond this, then we require the use of omega. All right. So here again we have the numbers, and it is interesting to see that the point Q4 indeed is achieved. So let me look for that. I don't see it. We see it here. The maximum rate that we can achieve is indeed the contribution of noise plus SNR21 plus the contribution of power of transmitter 2 plus the correlation obtained through omega. So this is the point here on the top. Now, the rate that we see here at Q6 is B2, and this is exactly noise plus contribution of the two transmitters due to the independence of these two signals, plus the part obtained with the correlation. And this, C, is a correlation that is due to only information transmission. All right? Let's see then the figure, this volume. Let's try to put some planes that cut the volume. So this plane in white give us all these information rates, and it corresponds to the information capacity obtained without any energy constraint. If we increase the energy demand to B1, we obtain another plane that cuts the volume, and then we obtain this gray plane that we see here that contains several points in the Pareto front in the optimal information sum rate, and then is completed here. If we continue increasing the energy rate, we will be a point at which we contain only one point in the Pareto front, which is this Q6 that I was pointing out before. And then after, when we increase up to, for higher values of energy rate, we obtain this darker square here, up to a point that this becomes the point that we see there. All right. So we have already seen why we obtain an improvement in the energy transmission due to thanks to feedback, and we see that let's say correlation between the two signals is not that strange for us, because we are used to the idea of feedback and using it for correlating the signals in such a way that the sum rate can be increased. And then we have the idea also of correlating the signals through the common randomness in order to achieve the maximum rates that we may imagine. Okay, so one natural question that appears here is whether or not this, let's say, help due to feedback is significant. So let's place ourselves in the points at which we are transmitting at the maximum information sum rate. So without feedback is the blue lines. There are two values of SNR. So all the SNRs here are the same. So that's why we obtain something very symmetric. And then when SNR is equal to this value here, we obtain this sum rate without feedback and this sum rate with feedback. So we increase now the energy rate, and what we see here is that there is a point at which, in keeping that let's say sum rate requires holding the energy rate at B. Going beyond the energy rate at this point here, that we call B and F to this term, requires reducing the information rate up to 0 when we want to go to the maximum. Now the same with feedback, which is the square. This is if we evaluate the energy rate that we can achieve at the maximum sum rate that we achieve without feedback, we obtain this square box here. Now, if we go to the maximum sum rate with feedback, so this is a little bit higher, unbounded, we know that this is essentially 0.5 bits per channel use in the case of 2 users. So this increase cannot be bigger than that threshold. Essentially, feedback doesn't help that much to increase the information rates. But we are going to study whether or not this is something significant in terms of energy rates. All right, so now we have explained these 3 points, and we are going to be interested in this gap, right? What is the increase in energy rate that we can obtain while still keeping the transmission at the maximum sum rate? So essentially, we are going to be studying what is this point BNF and what is this point BBF, right? So these are 2 energy rates that we will be studying. Well, it turns out that B of NF is achieved with independent signals, so we obtain only the contribution of noise plus the contribution of transmitter 1 plus the contribution of transmitter 2. That's essentially the value of BNF. The value of B with feedback then is equal to this. We have a correlation that is not the one given by Osarov, not the one obtained with omega, is exactly this value. So this is the value of the correlation needed between the channel inputs for achieving a rate that is equal to the sum rate without feedback. All right? So we are achieving with feedback the rate that we can achieve without feedback, but we are still using correlation. All right, so now let's take first, as a first test, the ratio between that energy rate with feedback and without feedback. Well, we obtain this expression here, and we see that this is bigger than 1. At a first glance, we obtain that conclusion. So what we can say is that indeed feedback is helping us to increase this energy rate. Now, how far can we go? Well, this depends of 6 different values of SNRs. So let's make it simple. Let's assume that we are going to have all the SNR possibly different, but we are going to study the system in low SNR and high SNR. Well, in low SNR, the conclusion is not very surprising. We essentially do not have an increase of that point B with feedback. It is, so the both points are equal. But in the case of high SNR, we obtain that this ratio is bigger than 1, but it is never bigger than 2, which implies that indeed feedback can at most double the energy rate. This is of course for the case of 2 users. We are going to see that there is a K factor if we are using K different transmitters. All right, so what we have here is a plot of the different ratios that we may achieve for different SNR. So as predicted, the SNR close to 0 is very small, and when it goes to infinity, well, we achieve the bounds that we have previously obtained. The bound of 2 is obtained when all SNRs are equal. Okay, so the expressions are in the paper. I'm not going to insist that much on this. Let's go to the break now. Let's keep in mind that we have then presented here all the fundamental limits of simultaneous information and energy transmission with a minimum energy rate, right? So we have presented that for the case with feedback, without feedback. We have seen how feedback helps increasing the energy rate. At very low SNR, that increase is not that significant, but when the SNR is sufficiently strong, we have seen that we can at most double the energy rate. All right, so let's stop here. We have a break now of 15 minutes, and then I wait for you here, guys. Thank you very much.